I hope on my side the question will come in from the backstage. What are the advantages of vertical GaN cathode technology compared to other device concepts?
Yes, there are different device concepts for vertical GaN transistors, for example, trench MOSFETs or other approaches like FinFETs. And the cathode is the only concept which has the same head restriction as a conventional HEMT with the same gate module. And also the different epitaxial layers are required for the vertical depletion zone. And the process technology is almost identical and can be adopted from the conventional HEMT technology. And this unique feature of the cathode opens a way to combine lateral HEMTs and the vertical device structure to realize like kind of vertical GaNPower ICs.
Okay, Michael. What will be the benefit for future devices and what application are targeted with the vertical GaN devices?
Yeah, the goal of the vertical devices, I think it's that the breakdown voltage can be increased without increasing the chip area compared to the lateral devices, and therefore a main target application of the vertical GaN devices are inverters, also in the automotive sector.
Okay. I forgot at the beginning to introduce Alfred. Alfred is the new member on my magazine. He will introduce himself shortly, and for the rest, we know each other well. We did not need to go to further introductions of ourselves. So, Alfred, it's your next question and a short introduction to the auditorium and to the speakers.
Okay, my name is Alfred Vollmer. Like Bodo, I'm an engineer, an electrical engineer, and I'm very interested in semiconductors. I have been a journalist for several decades already in the technical field. But while Bodo is located in the very north of Germany, I'm located in the Munich area in the very south of Germany. And yeah, we will work together because Bodo told me he needed more time to spend with his grandchildren, and that's why I stepped in. And I think now it's time to step in with the next question. And therefore, I'm a little bit prepared. Our latest issue is that one. Alex, you know it. There you had the cover page, the role of gallium nitride power transistors and integrated circuits in the emerging humanoid robot market. But why do you think GaN is so important to the development of practical humanoid robots?
So, I think that humanoid robots are here to stay because, we're all getting older and young people are not being born quickly enough to replace us. So there's going to be a gap, particularly at the more repetitive tasks in our society and maybe even taking care of older people. So I think humanoid robots are here to stay, and it's a growing market for a long period of time. And so we need to think about it. Now, what is a humanoid robot? It's something that is an untethered, battery-operated set of motors with a brain and maybe some eyes. So what's most important is you have to be able to make those motors imitate the functions of humans. There are linear actuators, there are rotating motors, They need to be able to grip things. They need to be able to hold things in place. And all those motor drive functions require precision. They require high torque. They have to be extremely efficient. They have to be lightweight and small. That's GaN. GaN does all that much, much better than silicon. Plus, you have the ability to integrate all those functions onto a single chip. So, we've for several years now been offering, we had it on the cover of our book. We'll shout out for our book here, but that's actually a monolithic power stage for a motor drive on the cover of the book. So we're able to integrate all those functions, make them tiny, tiny, stick a controller on it, a couple of capacitors, and a current sense, and now you have a motor drive that has the ability for very high torque, very high efficiency, high speed, and you can fit it inside the motor housing without any problem. So I think that's the big issue with humanoid robots is that they don't move fast enough, they're not precise enough. And we still need to develop all those technologies more, which is GaN. GaN is also in the eyeballs because those are LiDAR. GaN is also in the brain because that's AI. And today, if you use AI, those electrons go through GaN. So I think that GaN is just everywhere on these leading edge applications.
So there's a real gain through GaN, so to say.
I like that. I like that. I'm writing it down.
And you can always quote me with my name on it.
There we are. I like that. Marketing guy. Gain through GaN.
Okay. Yeah. So I think we got this prerequisite cleared, why it's so important. Now it's time for Bodo to ask the next question. Probably to Simon, I guess, but we will see.
Let's see what's popping up. It's to all of you.
Okay.
For traction inverters, considering today's GaN reliability, which type of GaN do you think will dominate the market, D mode or E mode? Schottky versus ohmic contact.
I have an opinion if you want to hear mine, but
Yeah.
I think that when you're talking traction inverters, I assume you're talking EV, which is 400 volts or 800 volts for the
Yeah.
larger EVs. In which case, silicon carbide is probably your best choice today. Now there's talk about vertical GaN, and I don't know how that'll evolve, but silicon carbide's a pretty good choice for today's traction drives, and that's why you see it beginning to dominate in there. And in the future, who knows? But I'm skeptical that GaN will have a significant role in that.
I would have some opinion about GaN in motor drives. First of all, that question was about the D-mode versus E-mode, right? Right now, most of the people prefer to use D-mode simply because people believe it is more reliable in the sense the D-mode itself is natural state of GaN. And so you only need to put it off with the cross pole or the direct drive. About the E-mode, usually people think the GaN itself is not so reliable. And also the threshold voltage is low. But we have come up with some IC, organ IC, such that we can increase that threshold. And then if you compare the figure of merit between the D-mode and E-mode, the E-mode is always few times bigger, better in the figure of merit. So I think in the long term, the E-mode is going to win this battle. About the reliability, the silicon carbide is of course more reliable because it has been around for much longer than GaN. But I believe GaN can also be reliable. If you look at the LED, which is made of GaN, it lasts for 20 years without breaking. So I think the E-mode GaN can do the same thing because E-mode GaN is from GaN itself. It's magnesium doped gallium nitride. So I believe in the long run, GaN is going to win over. But that's my view.
Yeah, I mean, I just have to insert, I just don't agree with what you say. I'm so sorry. But E-mode GaN, native E-mode GaN is phenomenally reliable, more reliable than silicon carbide, has fewer interfaces, and also it is as high current density, if not higher, than D-mode GaN. So I think that, you know, if you need to understand the modern E-mode device to understand that. Now, then there was a comment about low threshold voltage. Low threshold voltage isn't a problem. The problem in MOSFETs and in silicon carbide is the fact that threshold voltage goes down with temperature, whereas in E-mode GaN, it's flat. Also, the other problem is at lower threshold voltages that some people cite is this false turn-on from DVDT. And that has to do with whether or not you designed your device right. If you have a Miller ratio that's less than 1, you cannot false trigger. So the 2-volt threshold that E-mode devices have is a really good threshold voltage. It has low cost, low charge required. It is impervious to false turn on, and it doesn't have all these other quirks that MOSFETs and silicon carbide have in their threshold voltage. So you have higher power density in E-mode, you have higher reliability in E-mode, and you don't have an issue with that low threshold. And those are just myths that I just want to bust, and we've got plenty of evidence on it.
All right, Alex, I totally agree. I totally agree. I also meant to say that that was a myth. Yeah.
If I may chime in, I think there's still one fundamental question that has not been answered on there, and whether the D mode and E mode. And it also comes down to whether the motor drive, traction drive, is current sourced or voltage sourced. And when you have a voltage sourced system, that will prefer to use E-mode devices by its very nature. If you have a current sourced system, then it will prefer to use D-mode devices because you want your switches to overlap and to be conducting current at all times. So it comes also down to the end topology that would feed the motor. The most motor drives today are voltage source based, but the motors would actually work better if they were current source based, and there is some movement in that area in traction drives.
Thank you, Michael. Any more comments to it? Otherwise, we look for the next question to come up.
And this is a question that came through the chat. Thank you very much for all your contributions in the chat. And it says, as a circuit designer, I would like to be able to use both E-mode and D-mode. And to all now the question, however, I really miss a P-type device. When would you see this happening? Do you even need these for your goals and for your products? Who would like to pick up the question?
I can comment on that. If you are designing a low loss IC controller or a driver, P-type pads are very beneficial. But for power switches, I think N-type is good enough. That's my understanding. But look at silicon carbide and MOSFET, IGBT, it's N-type. So this is my comment. As for the availability of P-type GaN, there's a lot of university researchers. I think it's very promising, but now we kind of lack of motivation to develop P-type GaN for the IC, simply because silicon IC works so well. There's absolutely no motivation to do anything to try to replace it, except for the simple drivers or the current sensing and other simple functions. So this is my opinion.
So we certainly worked a lot, you know, on this issue. And I want to separate it. One is to be able to do the equivalent of CMOS. And if you can do the equivalent of CMOS in GaN, then you can address the digital world. And then there is the power P channel device, which is a different animal. The mobility of holes in GaN is very, very low, somewhere between 10 and maybe 50 if you're really smart. Whereas the mobility of electrons is 2,000. So it's not likely that you can make a power P channel P GaN device in silicon carbide or in gallium nitride. But in terms of CMOS device, there are many possibilities there, even with relatively low mobilities to do that. And there's several options on that we're working on. So I would say that there's a fair chance that we'll have a signal level P channel GaN device that will be economical in I'll say a digital circuitry, but not in the power world.
Okay.
I think it's time for Bodo again for the next question.
The question is addressed to the gentleman from Fraunhofer. What is currently one of the biggest challenge for vertical GaNPower semiconductors?
Yes, thank you for the question. So I think one of the biggest challenges for the vertical GaNPower transistors is the economic viability due to the very high wafer costs of gallium nitride wafers. So there are, of course, other approaches to fabricate vertical GaNPower transistors with 4H substrates like silicon sapphire and so on. But this brings other challenges such as dislocation, etc. So that is, in my opinion, the biggest challenge for the vertical transistors, GaN transistors today.
Thank you, Michael. Any additional comment from the presenters, from the speakers? So we can go to the next question. And Alfred, it's you again.
Okay, so this one goes to GaNPower, to Simon. Why is it important to increase the turn-on voltage and gate driving range for E-mode GaN FET?
It's very simple. I'm not as eloquent as Alex to convince people to use a 6-volt driving GaN, and it's only 1.2 volt turn-on voltage. Usually people are scared. The system people, they are scared, say, okay, it won't be reliable, and they have to redo all their drivers. So we came up with some idea to increase the driving voltage. Basically, you're going to have a voltage clamp. If you have a 15-volt signal, you're going to clamp it down to 6 volt, such that your main switch is still 6-volt driven. And but then there's also, because a noise in your signal, then the turn-on voltage at 1.2 volt is still a problem. So we thought, we came up with some ideas to use some IC, to increase that. Now, the big challenge is that if you do a lot of things at the gate, it's going to slow it down. What we found is that GaN is such a nice thing. And also the FUG of the main switch is so small. So the effect of adding a lot of IC but your gate size does not affect the speed so much. So if you say you're limited to within 1 megahertz of switching, so I think we have done our job. So we have come up with a 15-volt driving GaN, also with a high threshold voltage, as high as 4 volt. So our initial response from customers is very good. So here's the status.
Yeah, if I could jump in there, I think that the voltage limits on GaN are not a practical problem. Some people are afraid, as Simon said, but we've recently increased the transient overvoltage capability of our GaN to 7 volts. But really, we've never, ever in all these 15 years seen a single gate failure in the field. GaN gates are very robust. So I think that as more people gain experience, that fear level goes down. Also, today, they're all drivers. You can buy drivers from 20 different manufacturers, and they control the voltage on the gate. So it's really not an issue controlling it. And I'm speaking kind of in the lower voltages. Maybe at high voltages, there are different issues. But keeping the voltage on the gate low reduces your gate losses. And as we see people go to higher and higher frequencies, that gate loss is important. So you want to keep that gate drive around 5 volts. That's perfect. Never faults trigger, never fails. And your driver ICs will do that for you.
Alex, I partially agree. But if you have like 1200 volt device in an EV kind of situation, so maybe the tolerance of the gate needs to be increased. I know ETC is focused in the low voltage. Yeah.
Absolutely. Yeah. I qualify that as being in the lower voltages. This makes sense. In high voltages, it's a different world. And you're right. People are scared of those low voltages anywhere in a high voltage world.
Okay. I find it a lot easier to convince people to try GaN, for 800 volt device or 1200 volt device. They will be scared.
Okay, so I think it's time for the next questions. And please, all our audience is really welcome to type in some other questions that you would like to get answered. Go ahead, we are listening, and the experts will be answering.
Again, a question to EPC. What are the main obstacles humanoid robots need to overcome to gain widespread adoption, and how does GaN help? I think, Alex, you said quite a bit before.
Yeah, and we've been working, I think, with pretty much all the humanoid robot manufacturers today. And we've all seen the videos. And some of the videos are, I'll say, somewhat simulated. Some of them are real. And I think to most people, a couple of things stand out. One is these robots aren't smart enough. It's hard for them to learn simple functions like folding a shirt or putting something in a place. And that comes down to brain function. And brain function is improving through AI. The second thing is we all watch them walk, and they walk like very stiff, slow, and then when they have movements, they're slow. Some of the movements are slow because we're afraid that they'll hurt somebody. But a lot of that has to do with the two functions. One is that the sensors and feedback loops aren't fast enough to really give a smooth, rapid transition for the motors. And secondly, is the motor torque isn't enough to actually do that with enough precision that it doesn't hurt somebody. So we need to increase the motors. We need to increase the brain. And once we do that, then we'll need to reduce the cost. And I'll posit this to everybody here. You look at a robot today and they cost a lot of money. but there are fewer parts in one of those robots than there are in a car. So certainly they will cost less than cars when they go into volume. So motors have to be better. GaN helps with that. Brain has to be better. AI helps with that. Of course, GaN does that too. And then finally, we got to get the cost down, and volume helps with that.
Thank you, Alex. I think that answered fully the question.
Exactly. And that's the reason why we can go ahead and answer the next question. And this is a question to GaNPower, to Simon. Can GaNPower's GaNFET with gate regulator directly replace MOSFET or SiC without altering the driver?
Yeah, we have success convincing even the EV people, the manufacturing drivers to convert to just use existing silicon carbide or IGBT drivers to try to 1200 the 650 volt GaN, which fitted with the regulators. We plan to do similar things with the 1200 volt GaN. Okay, right now the 1200 volt GaN can only go to like 30 amp, this kind of level, so it's kind of too low for the motor drivers. We plan to increase that to 120 amp, and then when that fitted with a gate regulator that can directly replace the silicon carbide. Right now, it's more likely going to power modules, but it can also be some combination of discretes. So this is my opinion.
Okay. So I have another question to you, Simon. You mentioned your pin-to-pin compatibility. And
that means the direct plug-in, yeah.
Yeah, you mentioned that in your story. And in which way does this P2P, as you call them, technology enabled a more reliable gate driving? And why does it avoid compromising fast switching? Maybe you can explain this mechanism a little bit.
Well, yeah. When I say reliability, there are two levels. When you work with high voltage, the whole system actually have power voltage swings to like 1200 volt. So that's very serious. So if you have a low terminal voltage, so you're going to get into like control trouble. So this is kind of a reliability on the system operation level. So when I say reliability, I really mean on the system level, this GaN, the power switch, is more reliable. On the other hand, if you have more devices, more switches fitted within your power switch, just like in any other IC, the more components you use, the defects are going to add up. If, for example, with 10 devices to construct an IC, if one of them fail, it's likely the whole system will fail. So in a certain sense, that also adds the challenge to the material reliability itself. But if you look at the way that we construct the GaN regulator, we use the devices in the series. For example, we have you can think of that we have multiple FETs to increase the threshold voltage. if one of them fail, maybe the terminal voltage will drop from 4 volt to 3 volt, but then it's still very good compared to your original 1.2 volt. So I think in that sense, it's still more reliable than you only have the original thing.
Any comments from any other participators on that issue? No. So I think Bodo has a question already in the pipeline that he would like to ask.
It's again to EPC. What i.e. being central to humanoid robot function? How does GaN technology help meet the power demands of i.e. systems while maintaining efficiency and minimizing heat generation?
So, AI systems, which, we now hear more and more about, are based on a very power consumptive GPU chip. It started off a few years ago that NVIDIA made these GPUs in the H100 series that were really for gaming initially. Somebody found out that they were really good for artificial intelligence for a variety of reasons. And those are 300 watts. Then, because of the surge in demand for everything AI, they went to 600 watts, and their next generation, 800 watts, and their next generation is going to 1700 watts. The goal is to be able to, do as many teraflops as possible in a shorter period of time to process information intelligently. That means that they become more and more power consumptive. That means that they also are driven to lower voltages, which we're seeing from non-NVIDIA AI manufacturers like Alibaba. And all that means that you've got to be extremely efficient with power management, and your power management needs to be very, very close to your GPU so you don't get load line losses. All that's driving power density requirements, because you don't want, real estate on a server board next to a GPU is more expensive than real estate in London today. I mean, it's just very, very expensive. So things have to be small, and that means power efficient. They have to do more and more power. So 2 years ago, we were making 300 watt DC to DC power supplies for 48 to 12 conversion, 48 to 5. Now it's a kilowatt. And then we're already working on next generation with our customers for 1.5 and 2 kilowatts. That will not stop. It is all about how much computing power you can fit into how small a space. It's a performance issue with AI.
Thank you, Alex.
Yeah, so let me ask a question that I'm interested in. But first of all, this is your last chance to ask questions in the chat. We would really like to answer them. And my question comes back to Fraunhofer, because at the very beginning, I think there was a little hassle, Michael, with your computer. So maybe you can tell us a little bit more. Yeah, the question was, what are the advantages of vertical GaN cavity technology compared to other device concepts?
Yes.
Maybe you can outline it a little bit more.
Sorry, what? Maybe?
Maybe you can outline that a little bit more.
Yeah, there in literature there are maybe 4 major device concepts on vertical GaN transistors. So there are the trench MOSFET, FinFET, and one option is the CAVET. So it's an current aperture vertical electron transistor, and this special device has the advantage that it has the same heterostructure as the conventional HEMT. And so you can combine both technology, because the process technology is almost the same, but the epitaxial layers especially the depletion, the layers for the depletion zone are different. So you can combine both device concepts, so lateral devices with a vertical device with a vertical habit. And that's in our opinion a very good way to realize integration. So integration with lateral devices with a vertical power transistor, and that's the unique feature of this cavity device compared to the other concepts of vertical transistors.
Okay, thank you. So does anybody else have any questions to these gentlemen over here? If not, last chance. Oh, there is one question
Wait.
which just came in. Bodo, would you like to take over?
I take over.
Okay,
They just put it up.
okay.
It just came in.
We just have to prepare it, and then we will set it up for everybody to be able to read it on the screen, because it's much easier than to understand everything.
Back on the AI point, in the final stage, these systems require several thousand amperes at very low voltage. Can GaN deliver power at these low voltage?
The answer is absolutely yes. We have our new Generation 7 coming out, and at very low voltages, we are right at about 1 milliohm millimeter square. What does that mean? That means for a millimeter square device, you can do about a milliohm of on resistance. 10 square millimeters is 100 microohms. These are the kinds of resistances that are needed to conduct 1,000 amps. And this new generation, which we're starting to produce in December, by the way, is 100x away from the theoretical limit of GaN. So, you know, we cheer how great it is, but it can be 100 times better, and we will get there. So the answer is, if 1,000 amps can be done with GaN right now, 100 times better than silicon, and it can be 100 times better going forward. So look to GaN and forget about MOSFETs, their history.
Thank you, Alex. If there are no more questions in the loop, there is another question coming just now. My backstage gives me signs. So it's a question to GaNPower. In which way does the P2P technology enable a more reliable gate driving, and why does it avoid compromising fast switching? It's going to Simon.
Yeah, it's a good question. It's more reliable in the sense if you have a high voltage system, the voltage swing and the noise level is a lot. If we look at a lot of our testing environments, and the gate signal can be very spiky. Okay, you can swing, have this ringing from like 6 volt to 15 volt, 20 volt. When you have very spiky signals, then you always wish that this spike will not damage your GaN, right? So that's why this P2P technology have a gate regulator. You're going to put down, you're going to clamp down your noise to around 6 volt. That's why I say it's more reliable. Again, I already said that the panel voltage itself is also important. So as far as why it's not compromising the performance of fast switching, It's because it's all GaN, right? We all know that the GaN is much faster than MOSFET and also faster than silicon carbide. If you have several devices in your IC, it causes some delay. But it's still, again, it's still a much faster device than others. So even if it slows down a little bit, so if you're switching, it's below 1 megahertz, so there's no problem. Especially if you are going on an EV, it's only several K of switching frequency, so it's even less of a problem. So there's a limit, but if you want 10 megahertz, so I wouldn't bet on it.
Thank you. My backstage gives me the indication that there is no more questions coming in. And at that point, I will thank all of you for being here and making it a success, and looking forward to see you either at Electronica or at our wide bandgap conference later in December at the Hilton Airport in Munich. So have a safe day and enjoy life like we are doing. Thank you so much.